Hi everyone, welcome to Extreme Python 2024. Today I'll be talking on tackling thread safety in Python. I'm Adarsh, I'm a co-founder and lead consultant at Digio Labs. At Digio Labs, we help our global clients with Python and software development consulting. In today's talk, we will go over the concept of threading. Then we will take a look into race conditions, which are issues which happen in multi-threaded environments. Then we will take a look into synchronization primitives, which are tools that Python provides us to make our programs thread safe. Now let's start with threading. In Python, threading is a concurrency framework that allows us to spin multiple threads, and each of these threads can run concurrently, each executing its own piece of code. So why use threading? Threading helps us improve the efficiency of our application. It will help us with concurrent execution as well as improving the responsiveness of the application. Now let's consider an example. We have 10 available seats and we have a script for booking travel seats. We have the book seat function defined. If there are available seats, if the number of available seats is greater than 0, we are sleeping for a small delay to simulate some processing. We are deducting the available seats by 1 and we are printing a message indicating that seat is booked. If the available seats is equal to or less than 0, we will print the message that no seats are available. So there is an issue with this script. In the case of this script, bookings get completed sequentially. So only one user can access this Python script simultaneously. As a solution, we can think of trying multi-threading in this scenario. So to make our booking app multi-threaded, we are initially going with 10 concurrent threads and we are using a thread pool executor with our max worker count as the concurrent threads. So this means that there will be 10 concurrent threads. So a maximum number of 10 threads will be executing at the same time, and these threads tries to concurrently call the book seat function we have defined previously. Now let's see a demo of this in action. Here we have 10 available seats and we have our book seat function which is responsible for checking the availability and printing the booking message. Then we have 10 concurrent threads which will be the maximum workers in our thread pool executor. Then here we are creating 15 threads. There will be total of 15 threads of which 10 will execute concurrently, and these 15 workers which represent 15 customers will try to book their own tickets. Now let's execute the script and see what happens. So here you can see that the final seat count goes down to -5. So there are total of 15 users trying to book and each of them gets allocated the seat and the final seat count remains -5. Now let's see why this happens. The issue is because we have our total number of seats stored in a variable and concurrent read and write to this shared variable happens during execution. So this leads to something called race conditions. Now let's see what are race conditions. So a race condition occurs when the outcome of a program depends on sequence or timing of uncontrollable events. In our case, it's the thread execution orders. So in our flight booking application, the issue occurred because we had shared mutable data. We had our available seats variable, which is shared across all threads, and non-atomic operations get context switched. So there are like 15 total customers trying to book the application, and before one customer books and writes the available seats back to the memory, the process gets context switched and the control goes to the other thread. Now let's take a look into another example which will illustrate the concept of context switching. Here in this example we have a worker function which will get executed by 4 threads. It performs an iteration from 0 to 2. It sleeps for a small delay, and then it prints the name of the current thread which is executing this worker function, and it also prints the current iteration I value. So we have created 4 threads. We have a thread pool executor with maximum 4 workers, and we are creating 4 threads which will execute our worker function concurrently. Let's run this and see what happens. So we can see that initially worker 0 performs its first iteration, followed by the worker 1, worker 3, and worker 2. So all these workers perform its first iteration. Then similarly, each of these worker threads take turns to go through each of these iteration steps. So in this example, we can see that the execution is happening concurrently. Each of the worker threads are executing its operations in turns, and this happens due to a process called context switching. Here you can see we are printing sys.get switch interval value. Here you can see that the switch interval is 0.005. This means at the interval of 0.005 seconds, our Python interpreter will try to perform a context switch operation. So this will help us uh, give or yield the control to another worker thread which is waiting for its execution. So due to this process of context switching, each worker thread execute its own operation in turns. Now let's go to the concept of thread safety. A program is said to be thread safe if it can be run using multiple threads without any unexpected side effects or race conditions. So the booking example we have seen previously is non-thread safe. Then let's take a look into when we should worry about thread safety. We have like multiple concurrency frameworks in Python. So this is an image taken from Anthony Shah's talk in PyCon US 2024. These are the different concurrency frameworks. We can either use threading, coroutines, multiprocessing, or sub-interpreters. So the concept of thread safety happens when we are using multi-threading or threading as the concurrency framework. Next, thread safety happens in a multi-threading environment where there is shared mutable data as well as non-atomic operations. So in the concept of threads, threads do not have independent memory locations. They share the memory location of their parent process. So there can be issues when the data is shared across threads. And if the code executed with threads operates on immutable data, like there are no shared data and the operations are atomic, like when one thread completes its operation before being context switched, there won't be any thread safety issues. Now let's take a look into various options by which we can make our programs thread safe. First thing is we can go with any other concurrency framework, see if that's more suitable to our use case. Then we can go forward with uh, avoiding sharing of mutable data. We can use the concept of thread local data, in which case the data will be local to each thread and independent of other threads. Then another option is we can use synchronization primitives, which we will be visiting in the coming sections. Another option is to make operations atomic at the Python bytecode level so that they won't get context switched across threads. Moving on to synchronization primitives. These are tools provided by Python to make our programs thread safe. These are the synchronization primitives which are present in Python standard library, present in the threading module. We will go over each of them one by one. First, we have lock. A lock is a synchronization primitive that allows only one thread to access a resource at a single time. So a practical use case will be ensuring that only one thread can modify a shared variable at a time. This will help us prevent race conditions. So here is how we use lock. Initially, we will create a lock object by importing the lock class from Python's threading module. Then whenever we want to mark a critical section which could be executed concurrently by only a single thread, we can acquire the lock, and once our critical operations are completed, we can call the lock.release to release the lock. So within this process, only one thread will get executed before the lock is released. So when one thread acquires the lock using this statement, when other thread reaches this point of execution, they will get blocked, waiting for the lock to be released to continue their execution. In addition to the usage using the acquire and release calls, we can use the lock object as a context manager. We can use it with the with statement, and the block inside the with statement will be marked as a critical section. And when the code exits from this with block, the lock will be automatically released. Now let's make the previous booking application thread safe using locks. So we have our seat booking application. We will have 10 worker threads, and totally there will be 15 workers representing 15 users who are trying to book a seat at the same time. Then we will use a lock object to mark the critical section of the code. Now you can see the script has been modified from the previous form. We have the same 10 available seats. Then we are creating a lock object by creating an instance of threading.log class. We have a book seat function. Then inside the book seat function, we have our core logic for modifying the available seats, which is the critical section of our code. It is currently protected by a context manager block, which automatically acquires the lock when code enters the with statement, and it automatically releases the lock when the code exits out of it. Then everything else remains the same. We have 10 workers and totally 15 total number of users. Now let's run this. So you can see that only 10 seats gets booked, and the remaining seats will get 0 at a point, and the remaining 5 threads gets the message that no seats are available. So we stopped at the point where the available seat count became 0. Now we have our next synchronization primitive, which is rlock. The lock object we have seen previously is called a naive lock, because once a thread acquires a lock, even if the same thread holding the lock retries to acquire the same lock object, the execution gets stopped and it causes a deadlock. But in case of rlock, it's a re-entrant lock. So it allows the same thread to acquire the same lock multiple times without causing a deadlock. So this will be useful when we have a nested lock acquisition scenario, like when we are using recursive functions and a same lock object needs to be acquired multiple times. And the usage and everything is similar to that of the naive lock object, which we have seen previously. Now let's see a demo of the same. We have an example where we are only using one thread, and we have a function which acquires a lock and calls another function. The called function or the second function also need to acquire the lock. Let's see what happens in this scenario. So here in the initial case, we are using a naive lock or the simple lock object. We have two functions and we have only one thread, and it initially tries to call the book, flight, and hotel function. So in this function, we are acquiring the booking lock. Then we are calling our second function, which is the book hotel function. Inside the book hotel function, you can see that we are trying to acquire the same lock again. Let's see what happens when we execute the same. So initially you can see that the attempting to book flight is printed, then flight is booked, and now the hotel is attempting to be booked. So you can see that the book hotel function is called in our case, and our thread is now attempting to book the hotel. But the code gets stuck here because the booking log object is already being held by our previous function. And this execution stops indefinitely, and this condition leads to a deadlock. Now let's see what happens when we use an rlog. So the code and everything remains the same, but instead of creating a booking log object from the log class, we are using the rlog class in this scenario. Let's run this and see what happens. So in our case, the hotel booking also gets successfully completed because rlog is re-entrant. So it knows that the function currently holds a booking log, and when the same thread requests the same booking log again, the rlog allows it to take hold of the log in a re-entrant manner, and this booking goes through. So this is the scenario of nested log acquisition. So if we have like nested functions or recursive functions where we need to take hold of the log multiple times by the single same thread, we can use the concept of rlog in our scenario. Next, we have semaphore. Semaphore is like an advanced version of log. So it's a synchronization primitive that controls access to a resource by maintaining a counter, allowing a set number of threads to access the resource simultaneously. In case of logs, a log allows only one thread to access a critical section simultaneously. But in case of semaphore, we can maybe allow n number of threads. So we can set that 2 or 3 threads can access a critical section at the same time. So a practical use case is that we can use semaphore to limit the number of concurrent connections to a database to prevent overload. For example, in cases such as connection pooling. This is how we use semaphore. We can instantiate semaphore object by creating an object of the threading.semaphore class, and it takes the maximum allowed concurrent threads as its argument. In our case, we are allowing maximum 3 concurrent bookings. Then we can use it as a context manager similar to logs. We can use the with statement along with the semaphore object. So inside this block, we can enter our critical section, and since in our case the argument we have provided to the semaphore is 3, only 3 threads can execute this section, this with block at the same time, and other threads will get blocked waiting at this point in execution. Now let's see a demo of the same. Consider that we have 10 workers who are trying to book a travel package, 10 customers, and we allow only 3 concurrent bookings using a semaphore. So all these 10 workers or 10 customers try to book at the same time, but because of the presence of the semaphore, only 3 can book at the same time. So here we have maximum concurrent bookings defined as 3, and we are creating the semaphore object here. Now you can see that we are printing a timestamp followed by the waiting message, and this is our critical section. So only 3 threads can enter this critical section at the same time, and the booking takes 1 second. So whenever a thread executes or enters this critical section, it prints the booking message, and once it's about to exit, it prints the travel package is booked message along with the current timestamp. So you can see that we have 10 workers, and each of these tries to execute the book travel package function at the same time. Now let's run this and see what happens. You can see that at this same timestamp, all the workers started waiting. So this ended here in this code, but due to the presence of our semaphore, only three workers like worker 0, worker 1 and worker 2 got access to this with block and they started booking the trial package. So there is an initial delay of 1 second. You can see that at this timestamp ending with 31, worker 1 completed its booking, then worker 0 completed its booking, and worker 2 completed its booking. Now you can see that since three of the currently executing workers completed the booking, another three workers or the new workers 3, 4 and 5, they got access to this critical section and they started booking their trial package. So at the timestamp 32, you can see that worker 3, 4 and 5 has completed their booking, and then a new set of workers, another three workers could enter the critical section. So in our case, the usage of this semaphore ensures that only three workers could enter this critical section at a single point in time. Our next synchronization primitive is event. So event is a primitive that allows one thread to signal one or more threads that a particular condition has been met. So it can be used for signaling. For example, it can help us notify worker threads that new data is available for processing. Let's see its usage example. Here we have a flight landed event which is created as an instance of the threading.event class. Then we have two functions. First one is wait for passengers. We are calling the wait method on this event, flight landed event here. So at this point, our thread pauses its execution or it gets blocked waiting for the event to be set. Then we have the flight status update function, which is responsible for setting the event. Once this set method is called on the event, the execution or the thread can continue its execution, and this below code will get executed once the event has happened, which means we have set the event by calling the set method. Now we are currently not going to the example due to time constraints. You can access the example of the event primitive in the link which I will share at the end of my presentation. Next, we have barrier. Barrier is a synchronization primitive that allows multiple threads to wait until all threads have reached a certain point in execution. For example, we can use that in multi-phase transaction, so we can ensure that all worker threads complete their individual tasks before any of them can proceed to the next section. So here is an example of using barrier. Consider that we have 4 travelers and 1 travel agent. Here we are creating a barrier object by creating an instance of the barrier class. We are providing a total of 5 as the argument, 1 for the tour guide and 4 for the travelers. We have our traveler function and our tour guide function. So each of these call the barrier.wait function. So whenever this wait is called, the execution gets blocked until this wait is called at least 5 times, which is the value we have used to initialize the barrier. So the execution gets stopped until the wait method on the barrier object is called at least 5 times, and this line gets executed only when all travelers, which means total of 5 travelers are ready. Similarly, the code goes past the wait method call after 5 threads have completed the wait method call. Next, we have condition, our final synchronization primitive. So condition is a primitive that allows threads to wait for certain conditions to be met before continuing execution. A condition is a bit more advanced primitive, so it is associated with a lock and it comes with a lock object automatically, and it allows us for exclusive access to the resource once the condition is met. So a condition primitive is commonly used in producer-consumer scenarios. So it will help us pause a thread until a specific condition is met, such as waiting for a queue to be non-empty before consuming an item. So in this example, we can consider a scenario of customer service. We have a condition called customer available condition, which denotes that a new customer is available to be served. And we have a customer queue, it's the list for storing our current customers waiting to be served. We have our first function, add customer to queue. So here we are using the with statement with our condition object. So this acts as a log in this scenario. Then we are appending a customer, a new customer who arrives to this queue, and we are calling the notify method on the condition object. So we will see its usage in the coming slides. Next, we have the serve customers function, which is represents a customer service agent serving an available customer. So it runs in an infinite loop. So whenever a new customer arrives, we need to serve them. So this continues in an infinite loop. So here also initially we are acquiring the log using it as a context manager. Then if the customer queue is empty, we are calling the wait method on this condition object. This means that we are waiting here, or the execution waits here until another threads call the notify function which we have seen previously. Now let's take a look into these functions in detail. So we have our wait, notify and notify all methods. Also, we can see that condition object is associated with some kind of log. So it can also act as a log. We can pass a log object during its initialization, or one log object will be created by default by the condition. Now, coming to the wait method, the wait method releases the log and it blocks until another thread awakens it by calling the notify methods. So when one notify method is called, the execution continues. It reacquires the log and it proceeds with the next statements. Also, we can specify a timeout in the wait method. Then we have notify method. So notify method is used to wake up one of the threads who is currently waiting for the condition variable. And we have notify all method, which wakes up all the currently waiting threads for the condition variable. Now, summarizing everything we have seen. So we have seen that when moving to multi-threading, there can be issues such as race conditions, which can produce unexpected side effects or results. So whenever we are moving to a multi-threading model, we should keep in mind that the code we are working might not be designed for thread safety. This can even happen with standard library code as well as third-party libraries. So before switching to multi-threading, we should check for shared data, shared mutable data, as well as atomicity requirements of the application being executed. Then we should add synchronization primitives appropriately to ensure thread safety. As the CPython doc suggests, when in doubt, we should use a mutex or mutual exclusion primitives to ensure that our code is thread safe. That's it. Thanks everyone. You can get the talk materials and connect with me using the following link, linkhq.co/others. Thank you.